Okay, since we have missed a few days due to the snow situation, I thought I would do some quick videos here to kind of get you guys caught up. So we're not going to spend, a whole lot of time doing a 50-minute lecture on each section, but we'll at least go through the material and you guys can get started on the homework. So let's take a look at 5.1. Dealing with probability rules. Probability basically describes how likely it is that some event will happen. And of course there's a sample space, which is just a listing of everything that can possibly take place. And an event, of course, is a subset of the sample space. Now there are certain rules that we have to follow. One is the probability of an event here is greater than or equal to 0. That just means that all the numbers must be positive. And then this one here says that numbers have to be between 0 and 1. So things like 0.5 is a probability, 0.01 is a probability, 0.26. Okay, these are all probabilities, and you could do something like maybe that's even a probability. But anything that's negative, so maybe like minus 0.5, that's not a probability. Or anything larger than 1, so maybe like 1.01, that's not a probability. Okay? The other thing we must know is that the sum of the probabilities must add up to 1. So just to give you a simple example here, let's say that the sample space, let's say you toss a coin, the sample space of course would be heads or tails. And so then this is kind of like E1 and then this is E2. So then the probability of E1, which is heads, plus the probability of E2, which is tails, must be 1. And we know the probability of heads is a half, plus the probability of tails is a half, and that equals 1. So 1/2 plus 1/2 is equal to, so 1 is equal to 1. So that's basically what this rule says. Now there are a couple of different types of approaches that we can use. One is called the frequency approach. Now this is where you perform an experiment a whole number of times and then you just look at particular events that take place. And this down here is called the classical method, and this is where you look at the sample space, so you list out everything that can possibly occur and then you just count the number of ways that the event can happen. So we'll look at two examples of these different approaches. So let's look at the empirical approach. So one thing that you can do here with the empirical approach is I'm going to use a coin applet. So again, let's say that we want to know the probability of heads. Okay, and so what this says is, if we go back up here, then we're going to look at the total number of trials in the experiment and then look at the frequency of E. So what I've done is I've got this little applet here, and what we're going to do is we're going to toss the coin. Let's say maybe we toss well, just 100 times, so we'll just leave that as 100. Okay, so let's toss them. So here we go. Okay, so here we've got a sequence of heads and tails, and we know that the total number of reds and blues is equal to the total number of trials, and then the number of heads will be the number of blues. So you got this table here, and it just counts. So the probability would be the total number of tosses, 100, would be in the denominator, and then 47 would be in the numerator, and you got this ratio here. So you got 47 over 100, and that's what we're wanting here. So this would be 47 over 100. Okay. Now if you wanted to look at maybe probability that Steve Nash makes his next free throw or something, so let's just say probability Steve Nash makes a free throw. Free throw we'll abbreviate here. Well, that would just be the number of times that he's made a free throw. So the number of total number of of free throws that he's made, and then divided by the total number of trials, or the total number of free throws he's ever taken. So we'll say total number of free throws ever. Okay, and so that would give us a probability here. All right, so that's the empirical approach. So now let's look at some classical approach probabilities. So let's go to the next page here. Okay. Now, examples of classical approach. So let's say a coin is tossed 4 times, the number of heads and tails is observed. Okay. Consider the following events. Well, if we toss a coin 4 times and observe the sequence of heads and tails, we can get a whole lot of stuff happen. So one thing that could happen is they could all come out. So the first toss could be tails, the second toss, the third toss, and the fourth. Or you could get all heads. Second toss, third toss, fourth toss. Or you could get heads, tails, tails. Or you could get a whole bunch of others. So we have to have a systematic way of listing these out. And we use something called a tree diagram. So let's look at this, how we would do it here. Okay. And so tree diagram. This will help you sometimes. And so what we can do is we can say on the first toss, what happens? On the second toss, what happens? On the third toss and on the fourth toss. So here we can get heads, and here we can get tails, and then of course heads and tails here. Okay, heads and tails here, and heads and tails here, heads and tails here, heads and tails. Okay, and it gets kind of, it's going to get kind of tight here. Heads and tails, and we won't list all these out, but I'll show you how you can do this. Okay, heads and tails, heads and tails. So notice this first branch here is heads, 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 and then heads, 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 tails. All right, and heads, tails, heads, tails, heads, tails, heads, tails. Okay, you basically just go down each branch. So heads, heads, tails, heads, 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 tails, tails, heads, tails, heads, 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 tails, heads, tails, and so on and so forth. So let's go ahead and list this out. I've listed these out. You guys can practice this and try to list them out yourself. But I have them listed out here, and we'll just take a little picture of this. That way we'll have them. Okay. All right, so here we have the sample space. And once we get the sample space, then things are a little bit easier to the probability questions are a little bit easier to answer. Okay. So let's answer this first one here, at least 3 heads. Well, at least 3 means 3 or 4, and I'll just put a little red star beside each one. So at least 3 heads. This one is at least 3 heads, right? This one is at least 3. This one is at least 3. This one is not. This one is at least 3. At least 3 heads is here. At least 3 heads. And I believe that's all. So 1, 2, 3, 4, 5. So the probability here would be 5 out of 16. Okay, because there's a total of 16 elements in the sample space. Okay, so let's try another one. At most 2 heads. Well, at most 2 means 0 heads, 1 head, or 2 heads. So let's count these. At most 2 is here. At most 2 is here. At most 2 heads. At most 2 heads because it's 1 head. This is not at most 2. This is at most 2. At most 2. At most 2. At most 2. Most 2. At most 2. And this one is at most 2 because it's no heads. So at most 2 you can include this outcome with 0 heads. So now we get the probability here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So this probability is 11 out of 16. And then heads on the third toss. So let's see. Get rid of all these. And we'll count the ones head on the third toss. So 1, let's see, I'll just put a star, again a star. So heads on the third toss. Heads on the third toss. Heads on the third toss. And I believe that's it. Okay. 1, 2, 3, 4, 5, 6. Oh, we missed 1. Heads on third toss. So that's 8 out of 16. And then 1 head and 3 tails. So this one we can count up. So 1 head. So I'm just going to look for the one with 3 tails. So 1, 2, 3, and 4. So this will be 4 out of 16. Okay. So again, the sample space is really the most important part of solving a probability question. So let's look at one more here. So let's say John, Roberto, Clarice, Dominique, and Marco work for a publishing company. The company wants to send 2 employees to a statistics conference in Orlando. To be fair about it, they decide that 2 individuals who get to attend will have their names randomly drawn from a hat. Okay, so again, we have to list out the sample space, remember? And so let's go ahead and list that out. So we got John, Roberto, Clarice, John, Roberto, Clarice, Dominique, and Marco. And the easiest way to do it is just to pair it up. So we got JR, JC, JD, JM, and then we go to Roberto. We go Roberto, Clarice, Roberto, Dominique, and Roberto, Marco. And then we go to Clarice, Clarice, and Dominique, Clarice, Marco, and Dominique, Marco. And that's it. So now we can find the probability. So what's the probability Clarice and Dominique attend? Well, Clarice and Dominique, well, that's here. So 1 out of 10. What's the probability Clarice attends? Well, Clarice, she'll go, let's see here. So Clarice will go 1, 2, 3. So that's 4 out of 10. Just probability any other person will go too. So the probability 4 out of 10 they go, probability must be 6 out of 10, right? That John stays home, 6 out of 10. Okay. All right, so a couple examples of classical here. So what I want to do now is I'm going to let you do this one. I want you to practice this one at home maybe. Find the sum that the 2 die is equal to 1 to 12. So what's the probability? Right, the sum is equal to 1. Probability sum of the 2 upturned faces is equal to 2. And you'll do that all the way down for the sum. Probability, the sum is equal to 12. So that'll be one you can practice at home. Okay, let's move on to 5.2. And we're going to look at the addition rule here. So let's say that we've got a bag, poker bag maybe, that contains the poker chips from 0 to 9. We've got a sample space here. It's kind of like the bag. We choose a number less than or equal to 2, which would be the event 0, 1, 2. And F, choose a number greater than or equal to 8, which would be 8 or 9. And so let's draw these events out here. So we've got E and F. And notice how I draw these, E and F. 0, 1, 2, 8, 9. We call E and F, we call these disjoint because they have no outcomes in common. And when we have no outcomes in common, we can use the addition rule for disjoint events, right? These two events here are disjoint, so that basically just says we can take and add the probabilities. So the probability of E, of course, is 3 out of 10, plus probability of F is 2 out of 10, so 5 out of 10. Okay. Now we want to compare this with non-disjoint. Okay. So let's compare this with non-disjoint. Okay. So here we've got non-disjoint. Same sample space. This time we let even number be 2, 4, 6, 8. And F be a number less than or equal to 4, 0, 1, 2, 3, 4. Now watch what we do here. Here, this time when we draw the two events, we're going to have to be very careful to draw them as overlapping. So E and F. Okay, and the reason is because we've got some elements in common here. So in other words, if we draw a 2 out, it satisfies event E, but it also satisfies event F. So 2 and 4 go right in here, and then we'll have 6 and 8 out here, and then 2 and 4, and then 0, 1, 3. So 1, 2, 3, 4, and so 5, 6, 7, 8, and 5, 7, and 9 are still out here, right? Okay. Now these are called non-disjoint, okay? Non-disjoint. Okay, because they have something in common, right? It's an easy way to look at it. Now when this happens, we have another kind of rule here. And it looks like this, with this subtraction piece on the end. And so that essentially can solve this. Probability E, well, how many ways can E happen? 4 out of 10. Plus F is 5 out of 10. Minus E and F, which is 2 out of 10. Okay, so we get 7 out of 10 is the probability here. Okay, so you want to pay close attention to when they're disjoint and when they're non-disjoint. All right. Now the complement rule is basically just an event where you have E defined as some event, and then E complement is going to be everything else that's in the sample space, right? So if it's in E, it's not in E complement. So these are two events that are definitely disjoint. Okay, E and E complement are disjoint, right? They can't happen at the same time. So let's look at a couple of examples here. Okay, so let's say that the sample space is 1, 2, 3, 4, 5, 6. The event E is 1, 3, 5. So E complement is going to be everything else that's not 1, 3, 5. So essentially what you could do is just 1, 3, 5, just cross those out, and then everything 2, 4, and 6 is E complement. Okay, well if F is 1, 2, 3, 4, 5, then F complement is just going to be 6. Okay. Now the problem that I want to take a look at here in 5.2 is really just a what we call a contingency table. Okay, so let's look at this problem here in 5.2. Okay, so we have this contingency table, and we want to know the probability of getting a female. Well, the probability of a female is just going to be the number of females, right? Which is 115 divided by 197. Okay, probability, throw this one in, probability of a male, all right, is going to be 82 over 197. Okay. What about probability of one ticket holder? Well, we had 21 of those, 197. Okay. So what's the probability you get a female and a one ticket holder, right? The easiest way to do this is just to circle all the combinations. So we circle all the females, then you circle all the one ticket holders, and then the intersection of the two is the probability we're looking for. So that 14 over 197 is the probability that we're looking for. Okay, so let's try another one. All right. And this symbol here, you just replace this with and this one you replace with or. So the upward is or and this one is and. So it's a short way of writing these the ors and ands. Okay, now what about this last one here? Probability the driver's female or been issued one ticket. Well, these are non-disjoint, right? Because they can happen at the same time. So this will just be the non-disjoint rule. Probability of female plus the probability of one ticket holder minus the probability of female and one ticket holder. Right? We put this for the non-disjoint. So this event is non-disjoint. Okay. So the probability of female we found already, 115 over 197. Probability of one ticket holder, 21 over 197. Minus the probability of female and one ticket holder. Well, that's 14 for 197. So let's see what we get here. Okay. So this gives us 122 over 197. All right. So this is 5.1 and 5.2. So hopefully you will be able to do those, and I'll do another video about this same length for 5.3 and 5.4. So we'll see you guys next video.